Electric charge and force. Electric charge and force is the first unit in our electricity topic. We're going to start with what electric charge is and where it comes from within the atom. Then we'll talk about two different ways of transferring charge between objects, conduction and induction, electroscope, a way of measuring charge and its polarity, then Coulomb's law, the heart and soul of electricity. We'll talk about adding different electric forces from multiple charges, and then we have three fully solved free response problems. Electric charge and atomic structure. When you take two non-metallic objects and rub them together, you get an interesting effect. Before the contact, there is no interaction between them. Okay, we have a plastic ruler and some bits of paper. We then rub the plastic ruler on some fur. Afterwards, the two materials are attracted to each other. You can see the bits of paper going up, being attracted by the ruler. It has actually been known since ancient times that when certain materials are rubbed together, they develop an attraction for each other. You can see that today when you take clothes out of a dryer. In ancient Greece, people noticed that when thread was spun over a spindle of amber, the thread was attracted to the spindle. The Greek word for amber was electron, hence this force was called electric. Further experimentation showed that dissimilar materials would attract each other after rubbing, while similar materials would repel each other. These effects would not happen without the contact, and later, given enough time, the forces of attraction and repulsion would stop. This led to the thought that something was being exchanged between the materials. The something was later named charge. Because objects would be repelled or attracted, it was postulated that the charge came in two types. In the 18th century, American Ben Franklin noticed when a rubber rod is rubbed by animal fur, the rod acquires a negative charge, and the animal fur acquires a positive charge. When a glass rod is rubbed by silk, the rod acquires a positive charge, and the silk obtains a negative charge. Thus, two rubber rods after being charged would repel each other, while a rubber rod would be attracted to a glass rod. No new charge is created. Instead, it is just separated. The positive charge acquired by one object is exactly equal in magnitude, but opposite in sign to the charge lost by the other object. To understand where the phenomenon of electric charge comes from, the basic structure of matter needs to be discussed. All matter is made up of atoms, which are made up of protons, neutrons, and electrons. Each atom contains a central nucleus that is composed of protons and neutrons. Protons and neutrons are called nucleons. Electrons move around the nucleus in the empty space of the atom. This is not what an atom looks like. If an atom was to be magnified so that the nucleus was the size of a baseball, that's this thing right here, the atom would have a radius of 4 kilometers, and the electrons would be approximately the size of the period at the end of this sentence. Atoms are mostly all empty space. Since everything, including us, is made up of atoms, that means everything, including us, is mostly empty space. Protons and electrons have equal and opposite charge. By convention, as we discussed from Ben Franklin's work on charged materials, electrons have a negative charge, and protons have a positive charge. This is the origin of charges on material objects. Neutrons have no charge, they're neutral. Atoms are electrically neutral, not because they contain no charge, but because they have equal numbers of protons and electrons. Their total charge adds up to 0. If an atom gains electrons, it has a net negative charge, and it is called a negative ion. If it loses electrons, then it has a positive charge and is called a positive ion. The nuclei of atoms are much more massive than electrons. Each proton or neutron is roughly 1,800 times more massive than an electron, with each nucleus containing at least one proton. And yet, the charge on a proton is exactly the same magnitude as an electron. That's pretty cool. The nucleus is located deep within the atom, and the protons and neutrons are bound together by forces much greater than the attraction of the electrons to the nucleus. So, the charges that are free to move between objects are electrons. Like energy and momentum, charge is neither created nor destroyed. It is conserved. Opposite charges will attract and like charges repel. As a result, the negatively charged electrons are attracted to and bound to the positive nucleus. And once again, despite the great mass difference, the charge on an electron is exactly equal in magnitude to the charge on a proton, and that magnitude is denoted by E. The electron was discovered by J.J. Thomson in 1897, and in a series of experiments between 1909 and 1913, Robert Millikan and his graduate student Harvey Fletcher established the value of the charge E on an electron. Millikan and Fletcher's work and subsequent experiments established the value of E as 1.602 times 10 to the minus 19th coulombs. It has also been demonstrated that this is the smallest value of charge, with the exception of quarks, which are covered in more advanced physics courses, and all larger charges are an integral multiple of this number. So that's what we're going to worry about now. Because small amounts of charge can generate large amounts of force, charge is often measured in millicoulombs, where milli is 10 to the minus 3, microcoulombs, micro is 10 to the minus 6, and nanocoulombs, 10 to the minus 9. Solids are a form of matter whose atoms form a fixed structure. Nuclei, with their protons and neutrons, are locked into position. Solids are classified as either conductors, insulators, or semiconductors. In conductors, some electrons are free to move through the solid and are not bound to any specific atom. Electrons are bound to their atoms in insulators and may move short distances, but much less than the electrons in a conductor. Semiconductors, depending on their situation, act as either conductors or insulators. In conductors, some electrons are mobile and can move freely inside and on the surface of the solid. Copper wires, transmission lines, and metals such as gold. Insulators are materials that have strongly bound electrons that can move only short distances within the solid. Different insulators have varying levels of insulation capabilities. Glass, rubber or plastic like balloons here, and these are insulators that insulate power lines from lightning strikes. Semiconductors have properties of both conductors and insulators. These properties can be altered by adding small amounts of other elements. They are crucial to the operation of transistors, which are then used in cell phones, computers, recording equipment, music playback devices, and many other applications. Silicon and germanium are semiconductors.